Hello, this is Bhavya Kedar, and along with me is Ayush Patel. This presentation is about forest fire spreading simulation. It is a part of our modeling and simulation course. So, introducing the problem, we will be simulating a forest fire spread on a forest, which is basically divided into three different classes: tree, empty space, and burning tree. We will be using cellular automata for our simulation, and all these classes will be a bunch of cells of that grid. The forest trees are prone to burning because of the lightning strikes, and they can also catch fire from their von Neumann neighborhood. Uh, we will be analyzing the effects of various parameters like probability of burning and the time taken by a tree to completely burn down, wind and its directions. And we will vary all these parameters, and we'll try to look at the results and try to conclude. So the basic assumptions that are involved in this model are that all trees, burning trees and empty spaces in our simulation will be treated the same. So there are no differences between two different trees or two different burning trees or two different empty spaces. And the only von Neumann neighborhood is considered for propagating the forest fire. That is, the four neighbors, north, south, west, and east, are considered to be propagating the forest fires, and the other neighbors will not be playing any role in the simulation. Uh, all the trees, burning trees, and empty spaces are distributed uniformly throughout the forest. We have used a random function, and by using the probability, we have created the grid very randomly, which distributes these classes uniformly. And the cellular automata is assumed to have a periodic boundary. The reason for doing this is that the forest must be very large, and it cannot be contained in a 50 cross 50 or 100 cross 100 grid. So as to trying to imitate the real life conditions, we have used a periodic boundary, so as to simulate the results in a very uniform fashion. Again, we have not considered growth of trees into the empty spaces because the time of the simulation period is much lower than the time taken by a tree to grow. So it will not make any sense if we try to consider a probability of a tree growing into an empty space. So moving ahead, these are the rules that govern the cellular automata simulation that we are performing. If there are no burning trees in the Van Neumann neighborhood, then the tree will not catch fire from its neighborhood, and the only source of catching fire would be a lightning strike. The probability of any tree being prone the probability of any tree catching fire is 1 minus the probability of that tree being immune to the fire. So in the first scenario, when there are no neighbors, neighboring burning trees, the probability of the tree catching fire would be probability of the lightning strike multiplied by 1 minus probability of the tree being immune, because that is the only way the tree can catch fire in that scenario. And for the rest of the probability, the tree will not catch fire. In the second scenario, we can see one neighbor of the tree is a burning tree. So if there is any one or at least one neighbor, one von Neumann neighbor of the tree which is set on fire, then the tree will be catching fire with a probability of P immune, 1 minus P immune, and it will not catch fire with the probability of P immune. So these are the rules that will govern our simulations, and moving ahead. So let us simulate our forest fire spread model on a 50 cross 50 grid and see what happens. So for our first simulations, our parameters are P tree equal to 0.7, which means the forest is 70% dense initially. 30% of the area is empty, and out of the trees, there are only 0.5% trees that are said to be burning initially. Again, the immunity is 0.2, which means 20% of the time the tree will not catch fire from its neighborhood or from the lightning as well. The probability of lightning striking on a tree would be 0.1%. So as you can see, the forest fire spreads by neighborhood, and we can see the patches of green and yellow in our simulation. That is because the forest is being wiped out from the grid, and we still see some remaining trees burning. That is because of the lightning strikes that happen after majority of the forest is burned down. And this is how a forest fire propagates, and forests are being wiped out. Moving ahead to our second simulation, here we have considered the entirely dense forest, which ideally is not the case, but just for observation. The forest is 100% covered with trees, and there is only one burning tree in the center of the forest. The immunity and the lightning probabilities are not changed. So this is how the simulation would look like. So as you can see, only one burning tree was sufficient enough to burn majority of the forest. And this also shows us more the density of the forest, more are the chances of it being wiped out at the end of the simulation. Moving ahead, these are the curves that we have generated by simulating the cellular automata more and more times for different values of initial density of the forest. As we can see here, for a very great tree cover density in the beginning, uh, there is much more loss of the forest cover at the end. For example, the very first curve, the uppermost curve of this graph starts from the initial density of 1.0, which means 100% forest covers, and ends up at almost zero density. So that is how this works. For the forests of lower density, the burning does not make any difference to the overall density of the forest throughout the simulation. That is because the contact between trees decreases, and hence chances of spreading fire through the contact also decreases. And that is the reason we are getting these kind of curves. Again, we have simulated our cellular automata for different probabilities of the trees being burned down. Let us say if the trees are much more prone to catch fire from their neighborhood, as seen in the uppermost curve, with probability of burning is 0.9, which means 90% of the time it will catch fire from its neighbor if the neighbor is burning. And we can see for that curve, the most of the forest is burned down. The fraction of the forest burned down goes almost to 1.0, which means almost entire forest is burned down. So if the trees are more prone to catch fire from the neighborhood, then there are high chances that the entire forest is wiped out. Similarly, for the lower probabilities, such as probability of burning to be 0.1, majority of the forest is saved after the simulation. Moving ahead.
Now we'll see what happens when a tree keeps burning for a 2 time unit instead of one before it gets wiped out. So here are the parameters of our simulation. We have considered a grid where 75% of space is covered by trees, and 0.249 is the probability that a space might be empty, and a very little space will have burning trees. We have set probability of a tree being immune to zero, and also we have not considered lightning in this case. And here is the simulation result. As one can see, the whole of forest gets wiped out within a few iterations. That is because of a tree. That is because of the fact that a tree keeps on burning for 2 units, making its neighbors more vulnerable to fire. And here is the graph depicting the same. As we increase the initial burning fraction from 0.01 to zero point 0.1 for a fixed initial density of trees, the at the end of simulation, the remaining final density of trees decreases. And that is very intuitive because we have set the initial burning fraction to be high, which means that more trees are vulnerable to fire. And now we'll see what happens when the probability of a tree catching fire is directly proportional to the number of its burning neighbors. And and the parameters of this simulation is also the same, and we have not considered lightning in this case as well. And here is the simulation. As we can see, the number of trees at the end is higher than the previous, the number of remaining trees is higher at the end of simulation when compared to the last simulation. And here is the graph of this simulation, which depicts the trend, which depicts that the trend is somewhat similar to the previous simulation. Now we'll consider the effect of wind in this particular model. We have set the wind direction from north, south, east, and west at the beginning of the simulation only. And we have considered that when the wind speed is set to low, only one neighboring tree will catch fire, is prone to catch fire, and the wind speed, when the wind speed is high, two neighboring trees along the wind direction are prone to catch fire. And here are the simulations when the wind direction is from north to south for low wind speed. We can see that the spread of fire is somewhat similar to the earlier simulations. And when we increase the wind speed, the spread of fire drastically increases, and the whole forest gets wiped down, and the flow and the spread of the fire is also from north to south. And this simulation can be simulated for various wind conditions and wind directions from east, from south, and from west. And here are the conclusions of our simulation. As the initial density of the trees increases, the final tree density of the forest decreases because more trees are vulnerable to fire. And if any particular tree takes longer time to burn, they have higher chances of fire spreading because because they make their neighbors more time vulnerable to catching fire. And if there are more burning trees in the neighbor of a tree, then there will be higher chance of such a tree to burn down. And just like previous case, the forest burn drastically higher if the any if the external force do not intervene. And as we saw in the last slide, when we increase the wind speed from low to high, the whole forest gets wiped down. Uh, Thank you.